Another special case arises when phi minus psi is equal to 180 degrees. In this case, lambda optimum is 1 plus 1/2 psi, 1 over sine psi over 2. A2 is equal to sine psi over 2. And A3 is equal to square root of sine psi over 2 plus 1 times sine psi over 2. And A4 is equal to 1 plus sine psi over 2 in square root. In general, if corresponding crank angle is not important, meaning time ratio is not important, if you want to design for a certain swing angle, psi, centric forward mechanism is the best in terms of transmission angle. And this centric forward at the same time has the most favorable acceleration characteristics. This is something that I have discussed till now. In high-speed machinery, acceleration plays an important role. You don't want to have too high an acceleration at the output. The output angular velocity is not going to be constant, and it's going to change. And you want to keep the maximum acceleration within a certain limit. With centric forward, the maximum acceleration is the least for a given swing angle. Another thing is, if you have to have a certain angle phi, corresponding crank angle, meaning a certain time ratio, if that is absolutely necessary, in that case, select phi minus psi is equal to 180 degrees, meaning determine psi, the swing angle, accordingly. That will give you the best transmission angle characteristics. Okay, these are the two rules of thumb if you want to use it. Next, we are going to discuss the slider crank mechanism in a similar manner. In case of slider crank mechanisms, A2 must be less than A3, number one, and the difference between A3 minus A2 must be greater than C, the eccentricity. For crank, A0, A to be the crank. And furthermore, in this case as well, the dead center positions occur when the crank and the coupler are collinear. These are the two positions where the crank and the coupler are collinear. It forms a triangle, again, as you can see. The transmission angle is maximum or minimum when the crank is perpendicular to the slider axis. So cosine mu max is minus C plus or minus A2 over A3. Okay. Again, what we can do is write the loop equations for the extended and folded positions. They form a triangle, notice. We end up with these two equations. If we subtract these two equations from each other and let SE minus SF, meaning the stroke, is equal to unity, so that we determine the link lengths with S as unity, and then whatever the stroke we want, we can multiply A2 and A3 and C with that stroke to obtain the actual link lengths required. In that case, which we subtract, with this substitution, if we write the equation, subtract these two equations, we end up with this equation. These two equations subtracted. Now, what you can do is, again, we let z is equal to a3 e to the alpha e. This is z vector in extended position. A0, B0, AE is the vector. And lambda is equal to A2 over A3. Unlike the 4-bar case, in case of 4-bar, we defined A3 over A2, and lambda had to be greater than 1. In this case, lambda is equal to A2 over A3, and lambda must be less than 1. Using this z and lambda, okay, by the way, in this equation, we have A3, A2, and phi e as 3 A2, A3, and phi e as the 3 unknowns. We have one complex equation in this case. We have reduced these equations to 1. Now, we have one complex equation in 3 scalar unknowns. So we reduce them into one complex equation and one scalar. Substitute them into here, we end up with z1 plus lambda plus z1 minus lambda e to the I phi plus 1 is equal to 0. From which we can solve for z as such. This is again the equation of a circle in complex numbers. It is this circle, z circle. Since A2 over A3 is lambda, if I write 1 plus lambda z is equal to A2 plus A3, A2 plus A3 e to the I phi e. So it is another circle. Again, let me repeat, these are, if you invert the motion, keep the crank fixed, and look at the motion of the slider, these curves are the circle and center points. Ka is, and K0 are the circle and center points. When you draw a line from B0, it will intersect Ka circle at AE, K0 circle at A0. This is the slider crank mechanism that will satisfy a given swing angle, whereas the corresponding crank rotation is unity. We have taken it like that. If you want to increase it, multiply everything by S. Enlarge it. That's all. ZZ bar is going to give you A3. A2 is going to be lambda times A3. So A3 squared ZZ bar is going to give you A3 Z bar. If you take this equation, this time the first equation, SE plus IC, SE plus IC, minus SE plus IC is equal to BE A0 is equal to A3 plus A2 e to the I phi. Take its complex conjugate, SE minus IC is equal to A3 plus A2 e to minus I phi E. Okay, the complex conjugate of this equation. Subtract the two, SE's will cancel. 2IC is equal to A2 plus A3 e to I phi E minus A3 plus A2 e to minus I phi E. In terms of Z and lambda, I can write this equation as such. Z 1 plus lambda minus Z bar 1 plus lambda. Now, since Z is equal to this term, substitute it to obtain C is equal to 1/2 1 minus lambda squared sine phi divided by 1 plus lambda squared plus 1 minus lambda squared cosine phi. So we have z bar is equal to h3 squared. If we expand it, we obtain this equation. A2 squared is equal to h3 squared lambda squared, which we end up with this equation. We have a singly infinite set of solutions for a given phi. If you specify phi, you will end up with the values of A, C, A, and A2. A singly infinite set of solutions. For full rotation, let me repeat, C must be less than B minus A, C plus A must be less than B. And for pi over 2 must be less than phi, less than tangent inverse minus 1 over C. Cotangent squared phi over 2 must be less than lambda, less than 1. So we have a limit on lambda and we have a limit on phi. Okay? These are the two limiting conditions that you must be satisfied for a full rotatable crack. Cosine mu min, in terms of the transmission angles, if you substitute, notice we have, this is the equation. You have term C, A2, and A3 in terms of lambda, correct? And if you substitute those into that equation, we end up with cosine mu min is equal to this term. If you take the derivative of mu min with respect to lambda and equate to 0, again we obtain a cubic equation. T squared q cubed plus 1 minus t squared q squared minus t squared plus t to the fourth plus t squared plus 1 q plus 1 plus t squared is equal to 0. T is equal to tangent 1/2 phi. Q is equal to lambda optimum squared t squared. Now, unlike the 4-bar case, this equation, you can solve it analytically. And you have three solutions. Q1, 1/2, minus 1/2, plus 1/2, in square root 5 plus 4t squared. Q2 is equal to minus 1/2, minus 1/2, in square root 5 plus 4t squared. Notice these are. And then we have Q3 is equal to 1 over t squared. Q3 maximizes mu min. Minimizes mu min. I wrote it wrong. Oh. I wrote this wrong. I will change it. This term minimizes mu min. So that's out. Q2 gives you a negative value. Q2 gives you a negative value. Since both of them are negative value. Whereas the lambda optimum squared t squared. So lambda is imaginary. That's not a solution. So the only solution we have is Q1 minus 1/2 plus 1/2, 5 plus 4t squared is the solution for this cubic equation. Is the valid solution for us, from which we obtain lambda optimum squared is equal to 1 over t squared in square root 5 plus 4t squared minus 1. If you solve for lambda optimum squared, lambda optimum, for every value of phi, you obtain a curve like this. The minimum value of phi is 90 degrees. The maximum value of phi is 180 degrees. Okay? And you have max mu min curve as such. A over S, B over S, this has to be A2 over S. I think I wrote it wrong. A2 over S, A3 over S, or C over S is this. Notice A2 over S is almost constant at 0.5. Okay, it changes like this. Whereas B over S, A3 over S is changing like this. Okay, as you increase phi, that is going to go far. Okay, when you have phi is equal to C is equal to 0, C is equal to 0, it is centric, slightly cranking. This curve, this portion gives you the optimum, this line gives you the optimum, and these are the solutions for every cranking law. And C over S versus phi for mu min is going to be 0, 10, 5, 10, 20, etc. Goes on like this. This is the optimum.